Hi, I'm Andrew Netka. I'm going to be talking about split-slice training augmentation for RAKI networks. I have the shown conflicts of interest. First, a few words about simultaneous multi-slice imaging. In simultaneous multi-slice imaging, multiple planar slices are excited with a composite RF pulse. As such, a full integer acceleration is achieved in single-shot acquisitions like echoplanar imaging. SMS acquisitions yield aliased images which are reconstructed through standard parallel imaging techniques like GRAPPA or SENSE. This technology is central to modern neuroimaging research studies where high temporal resolution fMRI and high Q-space sampling diffusion acquisitions are necessary. The process of unaliasing is imperfect and can impact the subsequent modeling of reconstructed images. This residual aliasing is often called slice leakage in SMS acquisitions. A modification to the standard GRAPPA algorithm has been developed to mitigate this artifactual slice leakage. In the split-slice GRAPPA algorithm, individual case-based observations are modeled such that when the GRAPPA kernel is applied to a slice which is not to be reconstructed by the kernel, the resultant estimate is modeled to be 0, whereas when the kernel is applied to a slice to be reconstructed by the kernel, the resultant estimate of the modeled reconstruction is that case-base. Recently, deep neural networks have been proposed to effectively replace the linear GRAPPA kernel with convolutional neural network. A depiction of a RAKI network is shown on this slide. Different from other deep learning reconstruction techniques, RAKI networks are designed to be trained uniquely for each slice and coil of the imaging exam, just as GRAPPA kernels are uniquely fit for each exam. As such, this deep neural network is comparatively shallow compared to other solutions, so that the network can be trained in a short amount of time. The input includes real-valued representation of the acquired complex-valued multi-channel data, as real observations and imaginary observations for each coil are included as unique input layers. The output is the complex-valued case-space for a desired coil and slice. An interesting feature of a RAKI network is that it includes a convolution by a 1-by-1 kernel in the second-to-last or penultimate layer. There are many hyperparameters which can be considered with respect to the design of a RAKI network. The depth of the network, or the number of convolutional layers in it, can be changed. Here, a 4-layer network is shown. For each convolution, save the convolutions in the penultimate layer, the size of the convolutional filters can be changed, and this figure shows 9-by-9 filters. Also, the number of filters for each convolution can be changed, and those can be changed independently from the number of filters in the penultimate layer. This figure shows 64 filters being used in the convolutional layers and 128 filters being used in the penultimate layer. Further, batch normalization layers can be included in the network, and random dropout of neurons can be included in the training process. This work, a grid search over this parameter space, was considered. In the grid search, other RAKI hyperparameters were held constant. These included activation functions following all but the last layer, which were parameterized as standard ReLU activations. For the optimization algorithm, the standard PyTorch atom optimizer was used. The cost function that was optimized was the simple L1 norm. Because convolution is occurring in Fourier space, an initial parameter search showed that inclusion of bias terms can yield an artificial DC offset in the network output, an associated bright pixel artifact in the reconstructed image. For comparison, across a vast number of different networks, training time for each network was fixed to 300 seconds, with training occurring on an NVIDIA K80 GPU. In this work, we introduce ideas from split-slice GRAPPA into the RAKI deep learning reconstruction technique. This split-slice formalism essentially yields a form of training data augmentation for RAKI. The training data set for RAKI acquisitions can be considered as the data which is generally included in the GRAPPA kernel fitting. This network is supplied with an aliased K-space as the input and paired with the desired unaliased K-space as the output. This is depicted in the first line of the training data shown in this figure. For the split-slice augmentation, individual K-space data are summed across a subset of the slices in the acquired packet. Thus, for the second depicted training set, only K-space of the slice to be reconstructed is input, and that is same K-space is paired as the desired output. Further, the full set of 2 to the n training data sets includes some combinations in which the slice to be reconstructed is not included in the input, and these sets are paired with an array of zeros for the desired output. While the RAKI network can be trained with a single aliased dataset paired with the desired unaliased K-space, the split-slice formalism yields 256 training sets for an 8-band acceleration factor. So here's what we did. We trained 3,072 unique RAKI networks for each of 5 human participants scanned with the Human Connectome Protocol harmonized fMRI acquisition. The first 16 time points of the time series acquisition included a phase-taking schedule of the individual slices such that they could be unaliased via a Fourier transform along the temporal dimension, and those time points were used for RAKI network training. 20 time points in the series spread equally across the 5-minute acquisition and not included in the training dataset were used for testing network performance. The table of hyperparameters which were considered in this exhaustive grid search are shown at the bottom of this slide. Here are the results of the grid search, which show the impact of split-slice augmentation of the training data. These violin plots show the distribution of L1 loss function values across all networks and subjects of the testing data with the split-slice augmentation dataset shown in gray and without the augmentation shown in white. In this plot, the data are separated by the number of layers included in the RAKI network. Of note, a single-layer RAKI network with a single filter is equivalent to slice GRAPPA solved with the optimizer used in the neural network fitting. Of note, means, shown with dashed lines, are lower with split-slice training with 3 and 5 layers. Further, network performance is generally shown to be best with those 3 or 5 layers. Here, the impact of filter size is shown. In general, split-slice augmentation yields reconstruction loss functions in this training dataset that are lower compared to standard training across all filter sizes. Use of a single filter for each layer is clearly suboptimal, while increasing filter beyond filter sizes of 5 yields only minor changes. Here we show the impact of the number of filters on each convolutional layer on network performance and testing data. Regardless of the number of filters, improved performance is present with split-slice training augmentation. There is general improvement in network performance when more than 32 filters are used, and the distribution of network performance slightly shifts to a beneficial direction when more filters are used than that. In the penultimate layer of the RAKI network, filters of size 1 are used. In this plot, we show the impacts of changing the number of unity-sized filters in that layer. Again, split-slice augmentation is shown to be beneficial in each case. Similar to what was found with the number of filters in the convolutional layers, a modest number of filters, in this case 128 or more, are generally needed to see good results. Again, as seen in the number of filters in the convolutional layers, the distribution of performance across the networks improves slightly with more filters. Batch normalization is generally used in deep learning to reduce overfitting and improve network convergence by addressing internal covariance shift. Inclusion of batch normalization layers clearly improves network performance. Also, as noticed previously, split-slice augmentation yields improved network performance. These violin plots show the impact of training dropout on fit model performance. Clear differences in the impact of this technique to reduce model overfitting on split-slice versus standard training are apparent. With standard RAKI training, dropout yields improved network performance in the testing dataset. Conversely, networks trained with split-slice augmentation yield worse performance when dropout is included in the training time. Of interesting note, with the 300-second training time limitation, standard training, which includes only one training set, yields to the completion of 2 orders of magnitude more training epochs compared to the split-slice training. This difference is likely a key driver in this observation of model overfitting in this set of experiments. So there are a couple major take-home points from this work. Split-slice training augmentation is good. In nearly all cases, it yields improved performance compared to standard training, with the only major exception being tied to networks trained with dropout. This work suggests that overfitting is a key concern with RAKI, and that this issue can be addressed with techniques to reduce the probability of overfitting, including the inclusion of dropout layers in standard training, or the augmentation of training data, which is achieved with the split-slice formalism. Details regarding networks that perform best across all 5 subjects are shown in this slide. Of key note, differences in training data yield significant differences in optimal network parameters. Similarly, it is expected that such network hyperparameters should be individually considered for studies using other acquisition techniques, although this work focused on the de facto standard HCP acquisition. Thank you for watching my presentation. Please feel free to continue a discussion regarding this work in the comments below.